With OSPF, things are a little bit more complicated. It works differently than eIGRP, since it's a link state routing protocol, not a distance vector. I will show the point-to-multipoint and the broadcast network types in this video, because these are the most common implementations. So let's start with point-to-multipoint. And before we do anything, I shut down the tunnel interfaces and remove the eIGRP process from each router. So no router eIGRP DMVPN. And now let's start OSPF. Again, similar things. The spokes only form adjacency with the hub. They don't form adjacency with each other. And we only advertise the overlay addresses, not the underlay address. If you try to advertise the underlay address through the overlay address, that can cause very serious issues. So don't do that. So I enable OSPF on the loopback interface and on the tunnel interface. So router OSPF 1, network 5555, and I put everything in area 0 and network 10.0.0.5. And let's check the tunnel 0 interface. Do show IP OSPF interface tunnel 0. So the default network type on the MGRE interface is point-to-point. Obviously, only a single neighbor is allowed on the point-to-point network. So we will change that to point-to-multipoint. Interface tunnel 0 and IP OSPF network point-to-multipoint. So if I leave the network type as point-to-point on each spoke, because their GRE interface will also have the default network type of point-to-point. So if I leave it as point-to-point, we can still form an adjacency with the point-to-multipoint network on the hub. But we have to adjust the hello and the dead timers, because they are different on point-to-multipoint network. The hello timer is 30 seconds and the dead timer is 120 seconds. So I'm gonna change the hello timer to 10 seconds, which is the default value on the point-to-point network. IP OSPF hello interval 10 to show IP OSPF interface tunnel. And here we can see that the dead timer is automatically adjusted. It is 4 times the hello interval by default. So we are done on the hub. So I no-shut the interface and move on to the spokes. Router OSPF 1, and again we advertise the loopback address and the overlay address, or network 1111, which is the loopback address of spoke 1, and network 10.0.0.1. And do show IP OSPF interface tunnel 0, and the default network type for the tunnel interface is point-to-point with the hello timer of 10 seconds. So with the hello timer changed on the hub, we can now form an adjacency, which the routers have just done. And I just do the same thing on the other two spokes as well. So the hub has formed an adjacency with all of the spokes. So do show IP OSPF neighbors. And the spokes should have learned the routes of each other. Do show IP route, which they did, with the next hop address pointing to the hub. Just as with eIGRP, it is not a problem here, because all of the traffic goes through the hub anyway. Another possible solution is the broadcast network type. But with the broadcast network type, we need to elect a designated router. And as known, the designated router has to form an adjacency with all other routers. So since the spokes cannot form an adjacency with each other, only the hub can be the designated router. So with this network type, we need to ensure that the hub is the designated router. So let's change the network type to broadcast. I shut down the tunnel interfaces first. And I changed the network type to broadcast, so IP OSPF network broadcast. And we need to change the priority of the tunnel interface of the hub to ensure that the hub will be the designated router. So IP OSPF priority 255. I mean, as long as the spokes have the priority of 0, it doesn't really matter, but it's recommended to use the value of 255 on the hub. And I no-shot the interface. And let's move on to spoke 1. IP OSPF network broadcast and IP OSPF priority 0. So with the priority 0, we prevent that spoke 1 becoming the designated router. So any interface with the priority of 0 does not participate in the DR election. And I enable the tunnel interface. And we issue the same commands on the other two spokes as well. Do show IP OSPF neighbors. And again, the hub has formed an adjacency with all of the spokes. And actually, there is no backup designated router on this segment. All of the spokes are DR others. And if we check the routing table of spoke 1, he has learned all routes from the other two spokes, and the next hop address is now pointing to the spokes, not to the hub. This is an important difference. This is phase 1, so it doesn't really matter here, but this will be important in phase 2. So now I'm gonna remove the OSPF process from each router and we take a look at BGP. And we will be configuring iBGP in particular, because I have put all the spokes and the hub in the same autonomous system. This also allows us to configure dynamic neighbors on the hub. So if we add new spokes to the DMVPN cloud, the hub requires no additional configuration because we don't need to define static neighbor statements on the hub. Let's start with the hub, so router BGP 100, and we create a BGP listen range for the subnet 10.0.0/24, and with the peer group called DMVPN. So we establish new iBGP peering with any new neighbor from this subnet. So we don't need to add new neighbor statements if we add a new spoke router to the DMVPN cloud. And let's create the peer group on neighbor DMVPN peer group. The remote AS is the same, so 100. And remember, if an iBGP router receives an update from another iBGP router, it does not forward it to another iBGP router because of the iBGP split horizon rule. So we need to configure the hub as a route-reflector and every spoke as a route-reflector client. And by doing this, the hub will forward all BGP updates to every route-reflector client unchanged, so it won't change the next hop attribute. The next hop will point to the tunnel IP address of the spokes. So neighbor DMVPN and route-reflector client. And let's advertise the loopback address, which is 5555 with /32 network mask. And on spoke 1, router BGP 100, we configure static neighbor statements to the tunnel IP address of the hub. So neighbor 10.0.0.5, the remote AS is the same, and we advertise the loopback address, so network 1111 with /32 network mask. And as we can see, the adjacency is up. So I'm gonna configure spoke 2 and spoke 3 the same way. And let's check the routing table, do show IP route, and the spokes have the routes to the loopback address of each other, and the next hop is not pointing to the hub, but it is pointing to the tunnel IP address of the spokes 10.0.0.1, which is the tunnel IP address of spoke 1, and 10.0.0.2, which is the tunnel IP address of spoke 2. Alternatively, we can also advertise a default route to the spokes from the hub, like this neighbor DMVPN, which is the peer group, and default originate. So we don't really need to advertise individual prefixes to the spoke. All we need is a default route. So again, show IP route, and here we have the default route pointing to the hub. And finally, we are going to configure eBGP in the following setup. These spokes will be in the same autonomous system, because this makes us possible to use dynamic neighbors with the peer group on the hub. So I quickly remove the current configuration. Mono router BGP 100, and the hub again will be in AS100 or router BGP 100, and we create a listen range again, BGP listen range again for the 10.0.0/24 subnet with the peer group called DMVPN, and we create the peer group or neighbor DMVPN peer group, and the spokes will be in AS200 or neighbor DMVPN remote AS is 200, and that's all we need on the hub. Actually, let's advertise the loopback address as well on network 5555 mask/32, and no shut the tunnel interface, and let's move on to spoke 1. On spoke 1, all we need is a static neighbor statement, or neighbor 10.0.0.5, which again is the tunnel IP address of the hub, and the remote AS is 100, and we advertise the loopback address. The adjacency is up, so I'm gonna do the same thing on spoke 2 and spoke 3 as well. And let's check the BGP tables. On the hub, do show iBGP. The hub has learned the loopbacks of all spokes, but the spokes have not learned the prefixes of each other. They only learn the prefix of the hub, which is this 5555/32. So now they can't even reach each other. If I ping the loopback address of spoke 2, the ping fails, but the hub has all the prefixes in its routing table, so advertising a default route from the hub to the spokes could be a solution. So let's do that. Oh, neighbor DMVPN, which is the peer group, and the command is default originate. I forced to resend the BGP updates to the spokes, so clear IP BGP outbound, and now we have a default route on each spoke. It's also in the routing table, and we should be able to use this to forward the packets. So now the ping should succeed. So now these spokes can reach each other, but let's take a look at the previous problem. These spokes can't install the prefixes from each other into the BGP table. The reason is very simple. I will show you. Debug iBGP updates. So after issuing this debug, I resend the updates on clear IP BGP inbound. So spoke 1 receives the prefixes from the hub. Here is the prefix 2222/32, but we can't install this into the BGP table. The reason is very simple. ASPath contains our own AS, so they don't accept the routes of each other, but we can disable this loop prevention with the following command. Neighbor 10.0.0.5 and allowas-in. And look at that, prefix 2222/32 received. So now this should be in the BGP table, and it is. So now we need to issue this command on each spoke. And now if I take a look at the BGP table, we have all the prefixes, but we also have the default route, so it's not really necessary to receive the individual prefixes as well. But one more thing, the next hop, which points to the spoke routers, not to the hub. Again, in phase 1, it doesn't really matter, but it will be very important in phase 2, where we can establish dynamic spoke-to-spoke tunnels, and which will be the topic of the next video.